Welcome to the Crazy Hat Chemist. So another video here on solutions and their behaviors. Bam! So today we're talking about boiling point elevation and freezing point depression. The boiling point of a solution is always higher than that of the pure solvent. Okay, and here's the equation. The boiling point of a solution is equal to the boiling point N, that is the normal boiling point of the solvent, plus, notice the plus sign, is equal plus the delta, that is the change in temperature of the boiling point of the solution. Okay, and the change in temperature of the boiling point of the solution is equal to the K boiling point times I times molality. So what is the K? That is the constant for the boiling point. The I is the Van't Hoff factor. We're going to be discussing that in another video. And the M is the molality. Okay, and then here's this nice little graph here. Notice that the vapor pressure of the pure solvent is in the purple, and the vapor pressure of a solution is in the light blue, and the change in temperature is that difference right there. And so look at this here real quickly here. It's higher, and it's a positive sign, and it's a boiling point elevation. So notice the boiling point of a solution is always higher, and that's why there's a plus sign in between the boiling point normal and the change in temperature of the boiling point. And then notice it's circled to the boiling point elevation. That's a boiling point elevation. It's plus. Okay? And then we have the freezing point of a solution is always lower than that of the pure solvent. Okay, so the freezing point of the solution is equal to the freezing point normal, that is the normal freezing point of the solvent, minus, this is a minus because it's a lowering, it's a depression, the change in temperature of the freezing point of the solution. The change in temperature of the freezing point of the solution is equal to the delta TFPs of the solution is equal to KFP times I times M. And the K is the freezing point constant, the I is the Van't Hoff factor, the same I as in the boiling point, and the M is the molality, the same molality that we had before. And here, it's the same graph. Notice that the purple is the vapor pressure of the pure solvent in the purple. And notice that the light blue is the vapor pressure of the solvent. And there's a change between these two. And then notice this. It's a lowering, that's why the minus sign, and it's a freezing point depression, that's a lowering. Okay, how do you remember the delta T boiling point or delta T FP freezing point is equal to K IM? And that is, I went out with someone in college and her name was Kim. You just got to figure out if her name, her first name was Kim or her last name was Kim. But that is where it is. The K for the constant, the I for the Van't Hoff factor, the M, the little m, that's a lowercase m for the molality. Okay, so that's the change in temperature of the boiling point is the boiling point elevation, and the freezing point depression. We're going to do some mathematical examples of these really soon. This is a great application of chemistry. You can see that car overheating there, and then that ice cream maker right over there on the right hand side. It's why you're able to make ice cream even at, quote, room temperature by adding salt to that ice. And so your car doesn't overheat and boil over. That's why you're adding antifreeze or anything to that radiator so it won't hit that boiling point of water, which is 100, which is easily happening in California. Okay, I am the Crazy Hat Chemist, and of course I've got a crazy hat, and this is so far the best crazy hat here, and it is a lobster. Oh my gosh, rock lobster! If you like that video, give me a thumbs up. Give me a thumbs up. Subscribe to my YouTube channel, and I'm going to see you next time, and kind of hungry for some lobster tail. Bye now.